NEST 2018, right? So let's start the discussion now. Before jumping to the set, I just want to tell you that there are few questions which are not the part of the syllabus anymore, although there is the same PDF of the syllabus that is uploaded on the official website of NEST, but there is a link that is given just to refer in case to the rationalized syllabus, and they have clearly mentioned it that yes, we will follow the rationalized syllabus of the NCERT. So the topics which are not important, we are not going to cover. That means by that, which are not the part of the syllabus, right? So technically, moving to the question number 1, as these two questions are also not the part of your syllabus anymore, so that is why you can be lenient on them, but however they are quite general, so I just want to give you a quite glimpse that in first question says in H3PO4 and H3PO3 the number of pH bonds are respectively. So basically we know that H3PO4, H3PO3 and H3PO2 have the simple structure like this. So the number of pH bonds 1, and here the number of pH bonds 2, right? So if you try to see this question and the first question of IIT 2023, you will see something magical, right? Oxidation of NaBH4, the second question. The oxidation of NaBH4 with iodine results in the evolution of the gas X. So basically this is what I want to tell you, although it is not the part, but just for the sake of your understanding, that sodium borohydride is a reducing agent, iodine is an oxidizing agent. When they are treated together, what happens is basically technically you get a gas which is known as diborane, along with the evolution of hydrogen, right, and sodium iodide, right? This B2H6 is known as diborane, right? And when you treat it with ammonia, excess ammonia, then what you get is basically a compound which is known as inorganic benzene, very famously known as inorganic benzene. uh, Technically you get something like this, right? And each plus minus is cancelled out, so that is why the overall molecule is quite electrically neutral, right? So this is known as borazine. So what you get is borazine. So the option number B2H6 and B3N3H6 is correct. So this is what you get, right? And in the first one you have the count as 1 and 2 respectively in H3PO 2 and 1, right? So C option is correct. Now moving to the next question. The correct order of acidity is, now we know that for the comparison of acidity, we need to compare the stability of the anions that are found by the removal of proton. So basically we have this anion. After the removal of proton, we have this anion, not this exactly, we have got this O minus, we have got this sorry, SCN minus, and we have got this yeah, only these four. So we know that the order of stability for the respective anions is that SCN minus is most electronegative, most basically stable, followed by you have this one more is left, right? Which one? HCN, right. So you have this HCN as also as some anion, right? Cn minus. So the most stable is SCN minus, followed by your C triple bond N minus, because obviously a sp hybrid carbon with attached with the more electronegative atom like nitrogen, right? Then followed by your O minus, and then at the last your simple ethyne, right? So this is the order of stability of the anion. That is why similar is the order of their respective acidity of the parent acid. Now in electrolytic refining, you can just skip this question because this is no longer valid to be studied, right? This is basically from the metallurgy part, and you can be lenient on that. Yes, so this is a very nice question. You should try these. First of all, If you want to solve such kind of a question, you need to be very much specific. Bas. Thank you, thank you. If you want to basically solve this question, you need to be very much clear in what you are writing. So consider the chemical reaction P to Q being carried out in two different vessels, X and Y. So let's take two vessels, X vessel and Y vessel, and in both of them we are having the reaction P2Q, right? Now what they are saying is 1 liter solution in each of them is there. So basically the volume is same. Volume is 1 liter here, and here also volume of P is 1 liter, right? Now the reactions are started with 1 mole of P in X and 2 mole of P in Y. Means initially when the reaction was not started, initially you've got 1 mole of P here in the X container, and you have got 2 mole of P in the Y container. Now what you have done further, P is added continuously to both the vessels at the rate 1 mole per second during the first 2 seconds only. Means for the first 2 seconds you have added 2 moles, right? Because 1 mole per second, na, rate is 1 mole per second, and you got ultimately after 2 seconds here, somehow you have to get basically 3 moles, because you have additionally added 2 moles, right? And here you will get 4 moles. Now what you amazingly find out is, it is observed that P remains constant at initial value in both the vessels during the addition. It means that even if you have added 2 moles, it rapidly consumes, instantaneously get consumes, and again equals to the initial amount of P, and which means that 2 that you have added per second immediately get consumed to make the corresponding Q. So you will get 2 moles of Q after 3 seconds. After 2 seconds, what you will get is 1 mole again for the P, and the 2 that you have added per second will immediately be converted to the Q. So basically we understood one thing from here, that the rate of reaction is 1 mole per second. Means the conversion rate is 1 mole per second, right? Here similarly here will you will get the initial amount back, because 2 moles that you have added are rapidly converted here, and you will get 2 moles here, right? Now they are saying that if change in the volume is neglected, that is obvious, and instantaneous mixing is assumed, that mixing is very very rapid. The concentration ratio of P by Q at time t is equals to 3 seconds in vessel Y should be. So basically they are asking you after 3 seconds, yeah, yani ki this is at 2 seconds, right? So 3 second in upon finishing the third second, what you will get is another consumption of 1 mole, because the rate is 1 mole per second of the reaction. So when you basically proceed this reaction for one another second, what you get is this will be 1 mole left, and this will be 3 moles. So the ratio will be, ratio of P to Q will be 1:3, and that is what they are asking, right? So the answer is option number A. Now moving to the next one. Yeah, now the internal energy per mole of an ideal gas is denoted by E ideal, and for the same for the real gas, it obeying van der Waals gas equation, it is denoted as E real. Assuming the average kinetic energy of the molecule of the two gases at the same temperature to be equal, the correct statement for the gases at low temperature or low pressure is, so basically see, internal energy for ideal gas is basically, if you represent it with E ideal, right, is the sum of, we know that ideal gas for ideal gas in the internal energy is directly proportional to the kinetic energy, so we can just simply write it as E ideal is actually nothing but the kinetic energy of the system, right? And for, however, for real gases where you denote the internal energy by E real, we should have an idea that real gases, in the case of real gases, E real is equals to kinetic energy plus potential energy, because in real gases the intermolecular interactions also happen. So potential energy, and more often attractive potential energy will also be there, attractive potential energy, right? So now, since your ideal gas internal energy, yeah, the internal energy of the gas in case of ideal behavior is exactly equal to the kinetic energy, and the kinetic energy is same in both the cases that they have mentioned, that assuming the kinetic energy or average kinetic energy of the molecule of the two gases at the same temperature to be equal. Now we have to fetch for the correct statement. Now we know that we can simply write this equation as RE real is equals to E ideal, because this is equal to kinetic energy plus potential energy, but this, since this is attractive potential energy, this should be negative magnitude, so whatever value you place here, it will be negative. Following this, we got an idea that E ideal is basically greater than E real, and following to that, the first option is correct. Now if this is true, this cannot be true, right? Now E real decreases for an isothermal expansion, or E ideal increases for an isothermal expansion. Either of these could be if you proved either of them as true or false, then other one goes with the same relation, right? Now see, for expansion, what happens when you expand a gas? The attractive potential energy decreases, right? Attractive potential energy decreases because the molecules are separating from each other. It means that E real will increase, right? Because the factor that you are reducing is basically being decreased, right? So E real will be increasing, and similarly E ideal will, in case of E ideal, it will decrease. No, even in case of E ideal, since your E ideal depends only on kinetic energy, and at isothermal conditions kinetic energy is zero, the change in kinetic energy is zero, so you can say that E ideal ka jo change hai, E ideal, the change of E ideal will also be zero, so this is also incorrect. So both of these are incorrect statements, right? So the only correct statement is option A. Now moving to the next one. Consider a cyclic process P to Q, Q to R, and R to P for the system. Now see, whenever you want to consider a process cyclic, you need to understand that the last process is exactly the revert process. So if there are three processes, probably you are going to get two expansions and one compression. If there are four processes, you will get two expansions and two compressions. If there is a similarly, so this is how you need to understand that at least you need to have three steps to get a cycle. And if there are three steps, cycles will be expansion, expansion, then final compression back to the original position. And if there are four step cyclic process, then expansion, expansion, compression, compression, right? Are you getting me? So here there is a three-step process, and if we just try to understand all the cases, a in option A, they are saying that P to Q is adiabatic irreversible. Suppose this is adiabatic irreversible, straight line, right? Then Q to R is again adiabatic reversible. So expansion would be like this, Q to R, adiabatic reversible. So I just made it curved. And R to P, basically the back one, is adiabatic reversible. So if you apply adiabatic reversible compression here, so it will trace back the path. See, when you came from Q to R, it was adiabatic reversible expansion. Now they are saying that again do adiabatic reversible compression, so it will trace back you to Q, not to the P. So this is not possible here. That is why option A is the one that will not give you the cyclic work. For option B, you have P to Q as the same irreversible expansion adiabatic, and then adiabatic reversible simpler, and then at the last you have isothermal reversible. So isothermal reversible can trace back to P because the slope is different for isothermal and the adiabatic curves. Q to R is adiabatic, whereas R to P is isothermal. Due to the difference in the slope, obviously you can trace back to the position P. Similar to that, we have the C, where P to Q is again adiabatic irreversible, similarly. And then you have adiabatic reversible. And then you have isothermal irreversible. That is a straight line, although, but it can connect because of the different slope, right? So now, the last one. The last one, P to Q is isothermal irreversible, means isothermal, so relatively a lesser slope, but a straight line because it is irreversible. Then isothermal reversible. Isothermal reversible, similar but a lesser slope as compared to the adiabatic one. and then you have isothermal reversible. Now remember that adiabatic processes of expansion and compression exactly traces back each other, but for isothermal expansion and compression, this exact trace back does not happens, right? You have here isothermal reversible, here you have isothermal reversible. If you are thinking that P will retrace the path to Q, it will not happen because heat is not constant here. Heat is not constant here. In case of adiabatic, the net heat flow is zero, so the graph will follow the same curve to and fro. But in isothermal, it will need the rapid expansion or rapid compression requires the extent of change in heat. That is why this will definitely be tracing, will not be tracing the path back, and will immediately lead you to some way to the P. So cyclic process is possible in these three, but not in this one. So that is why option A is the correct most suitable option. Now moving to this one, this is a very simple question. So basically we all know that the reaction is basically similar to what we studied when we have this cumin and we try to oxygenate it, forms an intermediate cumin hydroperoxide, and when we do hydrolysis, what we get is basically this whole bunch of the molecule gets separated as ketone, and this OH gets attached to this carbon, and we get a phenol. Similar here, we will also get this whole bunch of the molecule will separate as a ketone, and this OH will be attacking as a and forming as a phenol. And there's the only difference that you will get a substituted ketone here because you have this two methyl groups extra. So very, very simple question, right? So you need to understand this. Now, so the option that is correct is B, right? Methyl isopropyl ketone and the phenol. Carbocations are important intermediate in organic reactions. They are often stabilized by resonance inductive effects and hyperconjugations. The cation that can be stabilized by hyperconjugation is, so you have to find out the cation which is solely which is one way or the other is getting stabilized by the hyperconjugation effect. This cation cannot have hyperconjugation because the attached carbon is sp2, and the chain continues. So nowhere it is like that you have a alpha hydrogen which could start basically hyperconjugation, right? Here, although this pi can be stabilized by the hyperconjugation of this methyl group, but this cation cannot because it is actually hindered by a sp2 carbon. So we need to have this interference cleared first, right? So this will not also be the responsible factor for the stabilization of cation, although this pi can stabilize this cation by resonance, but not this CH3 can do it by hyperconjugation, right? Now this one, clearly this cation cannot be stabilized by hyperconjugation because the next carbon is having no alpha hydrogens. This is the only one where hyperconjugation initiated stabilization of cation can occur, because this H3C will do hyperconjugation with this alkene, and following making this alkene basically pointing towards this carbocation and ultimately stabilizing it. So this can be possible like this. Suppose you have CHHH and you have basically a double bond, and then followed by you have a cation. So what happens is that it gives the electron, it goes here. So this is hyperconjugation, na? This is hyperconjugation. Technically you get a double bond here and you get a double bond here also, right? And you have a H plus at the periphery, right? So this is the hyperconjugation stabilization ultimately. So C can be the best option out of it, that will be stabilized by hyperconjugation. Now understand this. You have hydrogenation of cyclohexane and benzene. Hydrogenation of cyclohexane and benzene takes place as shown below. The resonance energy and of benzene is minus 36 kilocalorie per mole. Now see, very simple. If you have only one pi and you hydrogenate it, the energy that you get by making this is minus x. If there were three such pi bonds, what would you get? You get delta H is equals to clearly 3 times of this x, right? But if these 3 such pi are extra stable, suppose in order to break the pi you need to give extra energy, extra stable, and that energy is plus 36 kilocalories, right? 36 kilocalories per mole. So net delta H becomes minus 3x plus 36, right? So if this delta, so if this Y is basically minus Y is basically your delta H, obviously this is the energy, na? So this minus Y is basically minus 3x plus 36. If you just take the minus common or basically cancel it out, what you get is Y is equals to 3x minus 36. It means simply that the total energy that you've got by hydrogenating the benzene's 3 pi bond is not exactly 3 times of the energy that you will get by hydrogenating the single pi bond. It is actually slightly lesser. The amount by which this energy is less is exactly the main amount of energy that you have to additionally provide to break the pi bonds of the benzene ring because of the resonance stabilization, and that amount is 36. So this is how the relation was this. Moving ahead. Now complexes COX6 3 minus, COY6 3 plus, and COZ6 3 minus absorbs at 700, 475, and 310 nanometer respectively. The ligands X, Y, and Z most likely to be respectively. It's very simple now. See, all you have to do is you have to draw the 3 complexes COX6 3 minus, COY6 3 plus, and COZ6 3 minus. Now understand this. If it absorbs, so the lambda absorbed is, we should know that lambda absorb is inversely proportional to del O. Are higher the gap between the splitted d orbitals, more energy it will absorb, not the wavelength, right? So wavelength will be correspondingly very less. So if suppose they are saying that the complexes absorbs this COX6 3 minus absorbs 700 nanometer, this absorbs 475 nanometer, and this absorbs 310 nanometer, then definitely the gap of the del O will follow. This is del O. Let's say this is the first. Let's make it first complex, the second complex, and the third complex. Now the del O for first will be like this much, and then definitely as the wavelength is decreasing, the del O gap will be increased. So the del O will be more in the second complex, and for the third complex it will be even more, right? It will be even more. So all you have to arrange them in the increasing order of their del O. Now tell me, see, if they are clearly asking you for the effects of the ligand, right? They are asking you for the different effects of the ligands placed, right? So definitely they are placing the oxidation state same, because if you are already having difference in the oxidation state, how could you justify the effect of the ligand, right? So one thing needs to be constant. So oxidation state here in the metal should be +3 in all of it, because here we know that this is okay. All the examples are either anionic or neutral, and if you place here anionic, you will definitely get what? +3. So all the carbonyls are in +3, right? We can consider it to be assumption, right? Because we have to make the oxidation states equal, and the most probable oxidation state that you will get is placing these examples is +3, right? That you can surely see. Now understand, the difference in the strength of the ligands is exactly what going to make your del O sharply increasing. So respectively you have to tell them that this and this and this one, which order of the ligand is basically more correct. So if your lambda is decreasing, your del O here to here is increasing, right? So ligand strength is also increasing. Ligand strength is also increasing from left to right. So it means that you have to place the ligands all together in the increasing order of strength. However, here you have the highest strength, then low, and then lowest. So this is exactly reverse of the order, right? So this cannot be true. Now you should be aware of that fact that this thionide again, this NCS sulfur based ligand is very, very less as compared to nitrogen based ligand as per the spectrochemical series. So again, this is also not following the same order, that the complex first should have the lowest wavelength, lowest Delo, because of the highest wavelength absorbed, right? So it should be weakest, followed by this, and the most strongest should be at extreme right, right? And the only one that correctly follows is this order, because even this is not following that correctly, because both OH2 and OH minus will have almost comparable amount of the donating tendency, because the metal and the surroundings are almost similar, right? So this is the correct option that says that okay, this in the first complex COX6 3 minus F minus is basically, the weakest ligand. It will have the lowest Delo and the highest nanometer absorption, followed by NH3, which is relatively stronger, and followed by Cn minus, which is the most strongest ligands that will give you the maximum Delo and minimum absorption of the lambda. So this is the correct option, and this is how this was supposed to be done. Now moving to, yeah, consider a catalyzed reaction. So now understand, there's a reaction R to P. What they are saying, that consider the catalyzed reaction. Consider a catalyzed reaction R to P, right? So this reaction is actually proceeded in two ways, in catalyst, without catalyst, right? Done. So here the rate constant is K catalyst. Here the rate constant is K uncatalyst. Now we know that they are saying that however the catalyst becomes inactive at a temperature greater than equal to, यानी कि at a temperature greater than equal to 400 catalyzed reaction becomes uncatalyzed, because catalyst become inactive, right? So the graph that reasonably depicts the temperature dependency of overall rate constant K, simple hai. Now see, first of all, the reaction, the relation that basically relates the formula that relates the K with T is basically your Arrhenius equation. K is equals to A e raised to the power minus EA by RT. If you take log on natural basis, because we want to plot ln K, so it will be ln K is equals to ln A minus ka EA by EA by RT. Now you can divide it in on the basis of two particular cases, ln K catalyzed, ln A minus EA catalyzed, because activation energy is the main difference, right? RT. And here you can bifurcate ln K uncatalyzed is equals to ln A minus EA uncatalyzed by RT. Now we know that EA for catalyzed is lesser than, is less than EA for uncatalyzed, because obviously the main purpose of activation catalyst is to reduce the activation energy. So activation energy EA catalyzed is less than EA uncatalyzed. It means that slope of EA, the slope of catalyzed reaction less than slope of uncatalyzed reaction. Why? Because see, the slope is EA by RT. RT is constant, right, for a particular situation. So the slope depends on RT. T though is the variable with which you are plotting the graph. So the slope is EA by R, right? And R is constant. So the main thing that is deciding the slope is EA. Now, if the slope is lower, the EA will be lower, or vice versa. And since we know that for catalyst EA is lower, so the slope of this graph will be lower. So now they are saying that this value, this junction is 2.5, right? So now remember, this is one, what they are saying, that this 1 by T into 10 ki power 3 has a value of 2.5. This is what it means, na? Because the parameter is 1 by times 1 by T into 10 ki power 3. And the value of this entire factor here is 2.5. When you calculate, temperature becomes 400 Kelvin. So it means that below it, temperature is basically, you can say, greater than 400, and ahead from this, temperature is basically less than 400. So it means that in this factor, in this form, 1 upon t 10 raised to the power 3, the values which are having more higher values than 2.5 are the one where the temperature is actually less than 400. So here your catalyzed reaction is going to not work, so reaction becomes uncatalyzed. And here, sorry, here it is since less than so it will be catalyzed, and here it will be uncatalyzed. Now what they are saying, that the slope of uncatalyzed reaction is less, low slope, low slope, high slope, because more steeper. But this is incorrect. This is incorrect, because what we are saying, that for the catalyzed reaction the slope is less. So this is incorrect. Now similarly, this one, now see, there's a close call between this and this, because in both of them, where there's the temperature greater than 400, you have high slope, and as soon as your temperature falls below 400 Kelvin, since your reaction here becomes uncatalyzed, catalyzed, your slope gets lower. This is catalyzed, this is uncatalyzed, high slope, right, low slope, everything is perfect up to now, right? And this is what we are saying, that slope of catalyzed reaction should be less than slope of uncatalyzed reaction. But the only thing is that they are saying that while we are having uncatalyzed reaction, we are getting higher values of lnk, higher lnk, high lnk values. It means faster reaction, which is incorrect, because obviously catalyst is the one which will give you higher values of lnk. Otherwise what is the use of catalyst, right? It is going to make the reaction faster, right? But here they are saying that, yeah, okay, the slope is basically following the same thing that is theoretically predicted, but the values that lnk we are getting for the lnk is very, very less as compared to what we were getting in the presence of non-catalyzed reaction. So this cannot be true. So this is the correct graph in that sense, that for the temperatures, basically for the temperatures greater than 400, you have an uncatalyzed reaction, high slope, high slope, high slope, and relatively lower values of lnk. This is the max value of lnk that you are getting for a uncatalyzed reaction, right? So high slope and low lnk. But here this one having low slope, this one having low slope, temperature activated after temperature less than 400, right? And high lnk values at any point, then uncatalyzed. If you compare the lowest value of this catalyzed reaction, it will be still be higher than the max value of the uncatalyzed reaction. So this graph correctly says the thing. It says that, yeah, as soon as your temperature basically reaches 400, rapid increase in the rate is observed because of the presence of the catalyst, right? So understood this? Yeah. So, and graph will always be a decreasing slope because of the standard nature of this straight line equation. So this is the correct graph. Now this one, lnk versus same factor, but the values are from 0 to 2. Obviously it will be a straight line, because this is nothing but simple uncatalyzed reaction graph, right? Because till 2.5 you were having uncatalyzed reaction, so 0 to 2 you will also have this uncatalyzed reaction, so no variation of catalyzed uncatalyzed reaction will happen, only the uncatalyzed reaction simple graph that we usually follow for lnk and 1 upon t, right? So this is how correct options were: A was incorrect, B was correct, C was incorrect, and D was the correct option, right? Now moving on to this one. Now understand this. Three separate reversible processes 1, 2 and 3 are carried out with 1 mole of an ideal gas initially at STP. So three processes are there. In the process, the pressure P is measured while increasing any one of the quantities among volume, temperature and number of moles. So you have to see the variation of P basically as you increase the value of either of these three variables, keeping the other two constant, right? obviously. So if there are four variables PV and PV, T and N, you will see the variation of P with either of them keeping the other two constant, right? Plots of P in ATM versus X. X is your quantity among P, V or 1 upon what they are saying, that X is your quantity N, T or 1 upon V. Like, so you have to plot three graphs. You have to simply plot three graphs. You have to plot graph between P and N. You have to plot graph between P and uh, T, and you have to plot the graph of variation P and 1 upon V. And all of these three, for process 1 to 3, the numerical values of slope, now they are saying that this plot of P versus X are found to be linear. First of all, that all of them will be linear. All of them will be linear, right? And they are saying that either of them has the slope m1, m2, m3, and the order is m1 greater than m2 greater than m3. Now among these three, the one with the highest slope will be having the slope m1, and that will be the first process, it means. So all you have to identify is the process numbers, first of all, that out of which these three, which one is first process, which one is second, and which one is third, right? So that you could answer it. Now for that, you have to just understand that, okay, we have three processes, the three processes, right? Now first is P versus N. Let's suppose first is P versus N. So when you plot P versus N, what you will get is N RT by V as a constant term, right? P versus T, when you plot, you will get NR by V as constant term. And when you get P versus let's suppose 1 upon T, what you get is 1 upon V, what you get is P is equals to 1 upon V NR by NRT as the constant term, right? This is it. Now slope is RT by V. Slope is R by V, because N is 1. When it is constant, it is 1, right? When you're when you're specifically drawing the graph between P and N, then you cannot consider it 1. It is variable now. So the slope is RT by V. But in cases when N is constant, you can place it 1, because N is goes to 1, right? That is given. So here slope is RT. Now obviously, let this be X, Y and Z. So order of slope is, obviously the slope order is Z, X and Y, because here both the terms under multiplication, here both terms are under multiplication, but one form is there which is on divide. Here nothing that is multiplied, but there's one thing that is dividing. So obviously the smallest is R by V. So it means that this is m1, this is m2, and this is m3, because the order was m1, m2, m3. So it means that Z means P versus 1 upon V, yani ki constant T N is process first, right? And then followed by X, which is P versus N, process third, and then P versus T, process, oh, this is process second, and this is process third, right? Y, right? Now you got it. Process 1, P versus which one? Process 1, 1 upon V, P versus 1 upon V. Process 2, P versus N, and process 3, P versus T. Now this is what we have to understand. Now see, work done is 0 for the process 3. For process 3, the work done is 0. Why wouldn't we? Because for process 3, work done is 0 for process 3. 3 work done is 0. Wait, There's the issue, right? I guess I have done something wrong. P versus n, P versus n, RT by V, R by V and RT Z should be having M1. So M1 is Z, right? So it is the first process is P versus 1 upon V. Okay, P versus 1 upon V and RT, right? कुछ गड़बड़ हुई है क्या? RT, wait, this is RT, and the order is still M1, M2, M3, 0 for process 3. What is that process 3? Process 3 is constant T and constant. Oh, obviously, na. Right. It is correct. See. We are right. So P versus T graph, right? So it means that volume is constant, and since volume is constant, so work done is P delta V, right? So delta V is 0 because volume is constant, so work done is also 0, right? So obviously, this is the correct option. Heat is completely converted into work for process 1. So this is basically isothermal, because at constant temperature it is happening. So it means the delta U here is 0. So, and we know that as per the first law of thermodynamics, delta U is equals to minus W. So entire heat is converted into work, or vice versa for process 1 is the correct option. Entropy remain constant in process 2. So here we know that P versus N, we have to plot the graph. So obviously as we increases the N, delta S will increase, because entropy is the randomization that increases within the increase in the number of moles of the gaseous particles. So obviously entropy is not going to be constant. The last one, the average speed of the molecules remains constant for the process 3. So here this is P versus T. As we increase the temperature, obviously kinetic energy will increase, and what you can say is V will also increase. V is the average speed, because obviously kinetic energy is increasing, so it is not going to be constant, right, for this process. So this is the correct options among A, B, C, D. 4. Now, a homogeneous mixture of the compound P, Q and R is spotted on a thin layer chromatography TLC plate. The TLC plate is made up of acidic silica. The spotted TLC plate is placed in a closed jar containing diethyl ether, means your solvent is diethyl ether, as a mobile phase element. As the element rise up the TLC plate, the compounds of the mixture separate and travel to different distances. Now, in such case, now you have to just remember one thing, that high non-polarity more distance in TLC plate. So the compound which is highly non-polar will travel more distance, and high polarity means least distance, less distance in TLC plate. Now you can answer anything on the basis of that. The separation on the compound depends upon their degree of adsorption. That is the basic principle of adsorption chromatography, right? TLC. The compound Q moves faster than compound P. Now let's see. Remember, the one that covers more distance moves faster, obviously, right? So it means that the non-polar one will move faster. So Q moves faster than P. So this is Q, this is P. So Q is basically relatively slightly more polar as compared to naphthalene, right? This is naphthalene and this is a substituted naphthalene. Obviously, due to this group, the polarity is high, so it will move slower. So Q moves slower as compared to P. So I don't think so that this is the correct option. This is incorrect. So the compound Q moves faster than compound P. No, because this is slightly polar as compared to P, it will move slower, right? Not faster. The compound R moves slower than compound P and Q, right? If R moves slower, then it must be more polar than P and Q. So this is R, this is P and Q. Obviously, this is more polar as compared to P and Q, because this NH2 group is definitely going to be more inducing more polarity because of its strong plus M effect and all those things. So obviously this is going to be more polar, and since it is more polar, it moves slower than P and Q, right? Now the compound S is expected to move slower than the compound R. Compound S is expected to be move slower than compound R, Yes, because it is more polar. Due to the more highly polar groups presence, this is going to basically be inducing more polarity. So it is highly polar. So it will move slower even as compared to R. So obviously this is correct, right? Now moving to the last question, that is simply basically, you know that this is nothing but if you remember, this is nothing but Williamson ether synthesis, and we know that although the Williamson ether synthesis follows predominantly SN2, but you know as your technically your the formation of carbocation is feasible because of the presence of polar solvent, and you can say right, this Br can be kicked out, right, and forms a carbocation which is stabilized by resonance. So SN1 is possible, right? So we follow SN1 here, and as per SN1 we know that the rate basically depends only on the substrate, and substrate is this on which this attacks, right? So which forms carbocation basically. If the concentration of allyl bromide is doubled, the rate of the reaction is doubled. This is true because the rate depends on the substrate's concentration. If the concentration of ethanol is doubled, the rate of reaction is doubled. No, because ethanol reaction is not depending upon ethanol, it is SN1. If the concentration of allyl bromide and ethanol are doubled, the rate of the reaction is quadrupled. No, but the rate of reaction is doubled. This is true, right? So this was your NEST 2018. Even though the exam was difficult, but if you have answered at least 10 to 11 questions correctly without basically doing any negative marking, I would say that it could be the safest score for you, right? So similar strategy you have to follow. You have to first check out what questions you can do, what you cannot, and you have to just invest time diligently on those which you can, and that try making that count at least more than 9, right? So out of 20, do not target all the 20, but target at least 10 to 12 questions without compromising with the negative marking. That is what your target should be in the next exam, right? Now okay guys, so see you, bye bye, tata, take care. Yep, see you.